Hello, curious minds! Before we dive into the mysteries of our universe, remember to hit that subscribe button and give this video a thumbs up. Today, we're embarking on an extraordinary journey into the realms of theoretical physics, exploring two monumental theories: the theory of everything and string theory. These theories, albeit complex, provide fascinating insights into the fundamental nature of our cosmos. So strap in, as we're about to take a thrilling journey into the world of theoretical physics. Ever since the dawn of human consciousness, we've been trying to make sense of the world around us. The quest for a theory of everything, a single theoretical framework that can explain all physical phenomena, has been a pursuit since the time of Albert Einstein. Einstein, renowned for his theory of general relativity, sought to reconcile this theory with quantum mechanics. His vision was a unified field theory, one that could encapsulate the vastness of the cosmos and the minuscule world of subatomic particles in a single elegant equation. Einstein's theory of general relativity gave us a profound understanding of gravitational force, explaining how massive objects like stars and galaxies curve space-time around them. It's a theory that works spectacularly well on a large scale, predicting the movement of planets and the existence of black holes with incredible accuracy. On the other hand, quantum mechanics rules the world of the very small, the realm of particles like electrons and photons, where the classical laws of physics no longer apply. Quantum mechanics has been astonishingly successful in its own right, predicting a host of phenomena to an extraordinary degree of accuracy. However, these two pillars of modern physics have proven to be fundamentally incompatible. They describe the universe in radically different ways, with general relativity painting a smooth, continuous universe, and quantum mechanics a choppy, discrete one. This has led to a deep schism in our understanding of the universe, a schism that a theory of everything aims to bridge. The theory of everything is not just a mathematical curiosity. It holds the promise of answering some of the most profound questions about the nature of the universe. What happened during the Big Bang? What's inside a black hole? Is time travel possible? These are the tantalizing mysteries that such a theory could potentially unravel. The quest for a theory of everything is one of the greatest unsolved mysteries in physics. The journey towards this ultimate understanding is riddled with complexity and controversy, but it's a journey that continues to inspire and drive the human spirit of discovery. Let's shift our focus to another fascinating concept, the string theory. At its core, this theory proposes a revolutionary idea that the fundamental constituents of reality are not point-like particles, as we've long believed, but rather one-dimensional strings. To visualize this, imagine if you could zoom into an atom, past the electrons, beyond the protons and neutrons, and even the quarks. What you would find, according to string theory, is not a set of distinct particles, but rather tiny vibrating strings. These strings oscillate at different frequencies, and it's these frequencies that give particles their properties, such as mass and charge. Now you might be wondering, why haven't we seen these strings? Well, that's because they're thought to be incredibly small, even when compared to atomic scales. To give you a sense of just how minuscule, if an atom were the size of our solar system, a string would be as small as a tree on Earth. But the string theory doesn't stop there. It further posits the existence of multiple dimensions, 10 to be precise, or 11 if we include M theory, a superstring theory variant. We're familiar with 3 spatial dimensions and 1 of time, but string theory suggests there are additional compact dimensions that we're unable to perceive. There are 5 different versions of string theory, each with its own unique aspects, but all sharing the central idea of one-dimensional strings. These versions are type 1, type IA, type DIYB, heterotic SO32, and heterotic E8XE8. And then there's M theory, which is believed to encompass all 5 versions, tying them together into a unified framework. While the string theory is compelling, it's essential to remember that it remains unproven. Several challenges need to be overcome before it can be confirmed, not least of which is the difficulty in testing predictions made by the theory due to the incredibly small scales and high energies involved. String theory, though still unproven, presents a radically different view of the universe. So how do these two theories, the theory of everything and string theory, relate to each other? Well, let's dive into this fascinating connection. String theory is often considered a strong candidate for a theory of everything. Now, you might be wondering, why is that? The answer lies in its unique approach to solving one of the greatest puzzles in physics, reconciling general relativity and quantum mechanics, the two pillars of modern physics. Let's break it down a bit. General relativity, brought to us by the brilliant mind of Albert Einstein, gives us a framework to understand the universe at its most massive scales. It's all about the big stuff: planets, stars, galaxies, and the vastness of the cosmos itself. On the flip side, we have quantum mechanics, which deals with the universe at its tiniest scales. It's the realm of particles, atoms, and the fundamental building blocks of matter. One of the most vexing issues in physics is that these two theories, as successful as they are in their respective realms, just don't play well together. They're like two pieces of a puzzle that, no matter how you twist or turn them, simply refuse to fit. Enter string theory. It proposes a radical idea. What if the fundamental building blocks of the universe aren't particles at all, but rather tiny vibrating strings of energy? This seemingly simple shift in perspective has profound implications. It allows for a mathematical framework where general relativity and quantum mechanics can coexist. It's a bit like discovering a translator who can interpret the languages of two great scholars who have been unable to communicate despite their vast knowledge. The translator in this case is string theory, potentially bridging the gap between the large-scale world of general relativity and the small-scale world of quantum mechanics. But remember, it's still a theory. It's a mathematical model that, while elegant and compelling, still has much to prove. In essence, string theory could be the key to unlocking the elusive theory of everything. Unraveling these theories could have profound implications. Let's delve into the world of what-ifs. What if we could prove these theories? The potential implications are mind-boggling. First off, the understanding of our universe would deepen significantly. We'd be stepping into an era where our knowledge transcends the boundaries of the observable universe. We'd know how the tiniest strings of energy vibrate to create the cosmos, and how the grand scheme of everything fits into Einstein's elegant equations. It's like deciphering the universe's secret code, unlocking an unprecedented level of understanding. Such a breakthrough could also lead to revolutionary technological advancements. Imagine harnessing the power of quantum mechanics on a practical level. Quantum computers, faster than light travel, even time manipulation could become realities, not just science fiction. The theory of everything and string theory could be the keys to a future that today we can barely fathom. But it's not all rosy. These theories are surrounded by controversies and criticisms. Some scientists argue that these theories are too abstract, too detached from empirical testing to be meaningful. They say that without experimental evidence, these theories remain just that: theories, not concrete science. String theory in particular has faced flack for its reliance on extra dimensions, which we've never observed. Critics argue that it's more of mathematical beauty than a physical reality. The theory of everything, on the other hand, is criticized for its ambition. The universe is complex, and some scientists believe that looking for a single theory to explain all its mysteries is a fool's errand. These debates are crucial. They keep our quest for understanding grounded, ensuring we don't get lost in the beauty of our equations and forget the physical reality they're meant to describe. Though controversial and unproven, these theories represent our best attempts to understand the fundamental nature of the universe. They push the boundaries of our knowledge and challenge us to dream bigger, to never stop asking, what if? In the grand scheme of things, we're just beginning to scratch the surface of understanding our universe. We've journeyed through the intricate and complex world of the theory of everything, a concept that seeks to unify all the physical phenomena under one single framework. A theory that hints at a universe far more interconnected than we could have ever imagined. And we've delved deep into the perplexing realm of string theory, where the smallest constituents of matter are not particles, but rather tiny vibrating strings of energy. These theories, as abstract and complex as they may seem, are fundamental in our quest to comprehend the cosmos. They challenge our perceptions, pushing us to question, to explore, and to seek answers. They remind us that our understanding of the universe is always evolving, always expanding, just like the universe itself. But this is not the end of the journey. Far from it. As we continue to probe the mysteries of the universe, these theories will evolve, adapt, and perhaps even transform entirely. That's the beauty of science. It's a never-ending quest for knowledge, a testament to human curiosity, and our insatiable desire to understand our place in the cosmos. Remember to stay curious and never stop questioning. Don't forget to like, share, and subscribe for more intriguing content. Until next time, keep pondering the mysteries of the universe.